Hi, Astronomy. This is Mr. Janowski. These are the slides from Thursday, January 7th, 2021. So, this is the class that I made optional given the bizarre events that happened in Washington at the Capitol the day before on January 6th, 2021. So, we started class. I reminded everyone that if you hadn't taken the quiz that was due that day, to take the quiz. Most people have done that by this point. And then we did the Kahoot again. We ended the previous class with the Kahoot. We didn't quite finish it, so we did it again. Good way to start and remind ourselves about things. Then we watched this video, this little TED Ed video, featuring this very bizarre looking animated person who lacks eyebrows. Yeah, watch the video. I'll put a link to it in the description. Um, touches on a lot of the bases we've been talking about the nature of light, how it works, and how it relates to astronomy. And again, yeah, if you're drawing a human face, it kind of needs eyebrows. Um, Otherwise, it gets weird. But I'm no visual artist. So after that video, we started talking about heat. So think of this idea: 100 degrees Fahrenheit isn't actually twice as hot as 50 degrees Fahrenheit, and 100 degrees Celsius isn't actually twice as hot as 50 degrees Celsius. Yeah, neither of those things is how it works at all. However, 100 Kelvin is twice as hot as 50 Kelvin. And I pointed out, too, that for whatever reason in science, the convention is if you're using Fahrenheit or Celsius, you do use the degree symbol. If you're using Kelvin, you don't. So it's 100 degrees Celsius, but it's really just 100 Kelvin. I don't know why. It's weird. Anyhow, here is Lord Kelvin. And yeah, the important idea and the reason that makes the Kelvin temperature scale so useful for science, especially chemistry, is that 100 degrees Kelvin actually is twice as hot as 50 degrees Kelvin. Basically, math works correctly. The numbers mean what they mean. So, what do I mean by that? The Kelvin temperature scale directly relates the temperature to the energy of the substance, and the energy of the substance is really the average kinetic energy of the particles. So in this animated GIF right here, we've got, this is meant to represent a bunch of gas particles, just roaming around inside of a box. And so they're all moving around. They have kinetic energy. They're moving at different rates. Some are going faster than others, and then they bump into each other, and some speed up, some slow down, all that stuff. So they're not all going with the same velocity or the same kinetic energy, but they have the same average kinetic energy. Well, I shouldn't even say that. There is an average kinetic energy. And that's what temperature really is. It is the average kinetic energy of the particles that you have. And it's most easily understood if you're looking at particles of a gas. It's just how quickly they're all moving is related to their kinetic energy, and it's related to their temperature. And this is what makes the Kelvin scale so very good. So if the particles had no kinetic energy, and ignoring the quantum weirdness that makes that slightly impossible, if they had no kinetic energy, their temperature on the Kelvin scale would be zero. That is what absolute zero actually is. Let me go back to this picture. Yeah, so if you could imagine all these guys slowing down until they were all just completely stopped, what would be the temperature of that thing? It would be absolute zero, 0 Kelvin. And that's why there is an absolute zero, because you can't be moving slower than stopped. And stopped means 0 Kelvin. If, however, they were moving just a little bit, they might have 1 degree. I'm sorry, I said it wrong. They might have a temperature of 1 Kelvin. If they were moving around with twice the kinetic energy, well, they would have twice the Kelvin temperature. It would be 2 Kelvin. And if they had, 50 Kelvin, which is actually a very cold temperature, they would have a certain amount of kinetic energy. If they had twice that kinetic energy, their temperature would be twice of 50. It would be 100 Kelvin. So here are different temperatures on the Kelvin scale. It's wonderful to use in science applications. It's not a very practical one for day-to-day things, because 0K is absolute zero. Water freezes at 273 Kelvin. So 273 Kelvin, well, 273 temperature-wise sounds hot. 273 Kelvin is literally freezing. That's 0 Celsius and 32 Fahrenheit for us Americans. Room temperature on the Kelvin scale is about 293 Kelvin, and water boils at 373 Kelvin. So for day-to-day living, the Celsius scale would be best. That's what most of the world uses, where water freezes at 0 and it boils at 100 degrees Celsius. Of course, in Fahrenheit, water freezes at the nice round number of 32 degrees Fahrenheit, and it boils 180 degrees higher for some reason at 212 degrees Fahrenheit. So, yeah, whatever. Fahrenheit's silly. Celsius is better. If you're doing science, Kelvin is the best. And now to astronomical things. The surface of the sun is a pretty warm 5,800 Kelvin. The core of the sun is much, much hotter. It's 15 million Kelvin. So when someone says, how hot is the sun? Well, it depends very much what part of the sun you're talking about. So heat, temperature, and radiation. When hot objects emit light, and you can see this if you turn on your electric stove. So if you have this kind of, electric range at your house, if the stove is off and it's cold, it just looks like a flat black color, and it doesn't seem to be shining at all. If you turn it on, you're going to heat something up. After a little while, it starts to get kind of dimly red, and then it gets redder, and then it gets reddish orange, and maybe it might get up to orangey yellow, and that's as hot as a electric range top is going to get. It'll look orangey yellow. So yeah, you're familiar with this idea that hot objects emit light. So why don't you emit light? Well, in fact, you do emit light. However, you're not as hot as a turned on electric range. What that means is most of the light you're going to emit is in the infrared part of the spectrum. So you are emitting light. You can see that in this picture taken with an infrared camera. The person's hand is glowing with light, but it's in the infrared, and your eye can't see it. The fact that your eye can't see it doesn't make it not light. It just makes it light that you can't see. The infrared camera can see it. And this salamander, lizard, I don't know what it is exactly. It is noticeably colder than the person's hand that's holding it. That's because reptiles and amphibians, they're cold-blooded. They're only as warm as the outside temperature, whereas humans and other warm-blooded things, mammals and birds, we generate our own internal temperature. And I rambled on about this a little in class. Basically, there's pluses and minuses either way. But yeah, that's why if you looked at them with an infrared camera, the warm-blooded thing, it's warmer. So it's going to be glowing more brightly in the infrared than the cold-blooded thing is. So as an object's temperature increases, it radiates light more strongly at shorter, higher energy wavelengths. This is true of all hot objects, and this is very useful in astronomy because it allows the astronomer to measure the temperature of stars and other objects just from their light. So if you want to know the temperature of a star, you absolutely cannot fly to the star, dip your thermometer in it, and see what your thermometer reads. That just doesn't work. But you can still tell its temperature very precisely just by staying where you are and looking at the light and analyzing the light from that thing very closely. So in this image here at the bottom right, in this little graph, we have the wavelength of the light that is being emitted. So 0 nanometers over here, up to 400 is violet. So here's the visible light. 700 is red, and then we get to the ultraviolets, X-rays and gamma rays out here, things like that. So yeah, those are the wavelengths of light. This is the part of the light you can see, and the vertical axis is the brightness. So how much light are you getting at each of those wavelengths? And on this graph, we have 3 different curves representing objects at 3 different temperatures. So look at the red one first. The red one has a temperature of 2,900 Kelvin. So this would be very hot to touch, but fairly cold as far as stars go. 2,900 Kelvin. And look at its curve. So its curve peaks out here at about 1,000 nanometers. So this particular object is putting out the most light in the infrared. However, it is still putting out some light in the visible, which means you would see this as something invisible light. So if you look at this picture over here, something that was 2,900 Kelvin would be here about, I don't know, 20% of the way into the picture. It would look something like that. If you had something that was hotter, something that was 5800 Kelvin, well, first of all, it's putting out more light. This whole curve is higher than the curve for the red object, so it is putting out more light, and its peak is at a shorter wavelength. So this thing at the higher temperature than this is putting out its maximum light at about 500 nanometers, which is right in the middle of the visible spectrum. And if you look at the other light it's putting out lots of light within the visible spectrum. So this guy here would be 5800 Kelvin. I hate that stupid thing that pops up. That would be somewhere near the middle of this picture. That is the color of light that this guy would put out. And then finally, you get to this guy, 11,600 Kelvin, which is on this picture. It's a little off this picture. It would be something out here. But notice the peak for this guy is putting out its maximum light actually in the UV. So its peak is at a wavelength, 250 nanometers, that is shorter than you can see with your naked eye. However, it is still putting out a ton of light within the visible spectrum. It's putting out more light at the shorter wavelengths, so more towards the blue end, less towards the red end. And that is why that kind of light looks very blue. Now, technically, all of these light sources and all of the light sources in the picture, they are all in some sense, quote, white, unquote. They are all putting out all the different wavelengths of the visible spectrum, but they're putting out different amounts of them. So notice the red one is putting out very little at the short end, so very little violet and blue, and it's putting out a lot of red. I mean, a lot of red compared to how much blue it's putting out. That is why this low temperature thing, if you look at its light, which is somewhere around here on the picture, it looks reddish. If you look at 5800 Kelvin, so that's right about here in the middle. So yeah, its peak is kind of in the blue. It's putting out plenty of light at the, the violet blue end, and also plenty of light over here at the red end. So that one's going to look kind of neutral in this picture. Technically, it depends on the white balance setting of the camera. Don't worry about it. But yeah, it's in the middle of this picture. And then finally, you get to this guy over here. So its peak is in the UV. But again, it's putting out a lot of light within the visible spectrum. It's putting out the most light here that you can't see, but it's still putting out plenty of light here. Notice how much more blue it's putting out at the short end, blue and violet, than it is at the long wavelength red end, which is why if you were to see that light source, which again is technically white because it's got all of the wavelengths within the visible spectrum, but it's got a lot more blue than it does red, so that guy would look very blue to your eye. So if you're into photography, I've just told you how white balance works for, the reasons of physics. Also useful for astronomy. So all that I just explained, that's what these words are saying. Now, in bold at the bottom, the question, what is the relationship between the peak wavelength? Remember, lambda is the symbol for wavelength. So the peak wavelength, lambda max, and the temperature. The higher the temperature, the shorter the peak wavelength. So remember the blue one. This was the hottest one. Its wavelength was the shortest. Its peak wavelength was the shortest. It's putting out the most of its light at 250 nanometers. The lower temperature guys, their peak was at longer wavelengths. I should be saying this the other way. Scratch that, rewind. Start here. The higher the temperature, the shorter the peak wavelength. So we'll start with the coolest one, and then we'll get higher temperatures from there. The coolest one, its peak, 1,000 nanometers. As you start to get warmer, 5,800 Kelvin, its peak is at a shorter wavelength. It's at 500 nanometers. And then you get to the hottest one on this graph, 11,600 Kelvin. Its peak has the shortest wavelength of the ones on this graph. Its peak is over here all the way in the UV at 250 nanometers. So then there's another video, which I will link to in the description. It's Okay to Be Smart, another smart YouTube channel that I like. Good host on that. It talks about, the history. How did we figure out what light is? Humans' idea of light over the millennia has changed a lot. And now we think we've got a pretty good grasp on it. We'll see. So again, to review, why do scientists prefer the Kelvin temperature scale? Because the Kelvin scale directly relates the energy of the substance. It directly relates the temperature to the energy of the substance, the average kinetic energy of its particles. Meaning that on the Kelvin scale, 100 Kelvin is literally twice as hot as 50 Kelvin, which is not true of the other temperature scales. The other question, as an object's temperature increases, at what wavelengths and energies does it emit the most light? As it gets hotter, it puts out more light at the shorter wavelengths, and these shorter wavelengths are the highest energy ones. So we had that graph, and again, we had this formula. As it's getting hotter, shorter wavelengths. Shorter wavelengths, meaning smaller lambda, will give you bigger energy. So that's how that works. And that's it for this part. Hopefully you found that helpful.